demonstrated that to you through a worksheet, that just by applying this simple rule, you're able to adjust your weights and the threshold automatically without doing any manual adjustment. Ultimately, your error became zero. That was important. And also in the last session, I explained to you about linear boundaries. So if you're doing any classification problem where your classes, it could be not just two classes, it could be more than that, but you're considering a simple example of two classes for the time being. But if your classes could be separated by single line in 2 dimensions, by plane in 3 dimensions, or what we call the linearly separable boundary in an n-dimensional space, then a single neuron, a perceptron, is able to solve your problem. If now this boundary is not linear, like we have an XOR problem, like I've explained to you, then a single perceptron is not able to solve a problem. You would have to start connecting neurons together to create like a team of neurons, if you can call it, or what's called as an artificial neural network, a network of neurons, which we'll consider today again. This is a fundamental understanding you need to have. So as you're learning about artificial neural networks or AI in general, especially deep learning, so whatever you're studying now in terms of perceptron and its limitation, but also its unique, very powerful features to classify linearly separable problems, that's a very important understanding to have. So as you read, you're going to see in the history of AI, you have the XOR problem. So you already know what the XOR problem is now. So it's important to know this thing. So I'm just going to share my screen now. I'm just going to share it again. Yeah, just going to share my screen and get started. If you have a calculator, a pen, and you need a piece of paper to do some calculations now, this is how I start, just to make sure you've got the fundamentals right from what we did last time. So do keep these things handy. Just sharing my screen now. I hope you're able to hear me well, and you're able to see the screen. If anything, I'd really do let me know. So I'm continuing from here. So we start with this simple exercise. Remember, we've talked about activation functions already, and the videos you've seen on YouTube, we've seen about what we call as activation of a neuron or triggering of a neuron to create an action potential on the output Y. Yep, and we've also seen you have lots of inputs. So what you see in front of you here is a simple neuron. We can symbolically represent it like this. You have one neuron, and then you have, in this case, 3 inputs. Yep, and the inputs have their values. And then what is written on these arrows are the weights. Yep, and then you always have a threshold theta. I've shown you what the effect of a threshold theta is. It basically shifts left or right to activation function. Let's try to do a simple calculation there. Let's say you have a neuron like this with 3 inputs, and the values are given here, and the weights as well. Remember, these weights are actually the intelligence in the neuron. Yeah, because these weights would decide how much weightage is applied to each of the individual inputs to be able to create a capital X, what we call a weighted sum of your inputs. And then you will always subtract your threshold and then apply your activation function. So let's start with a step function. Yep. So I would invite you. So once you've got your answer, I would be very happy to see your answers in the chat. So let's say you're given a problem like this. You have 3 inputs, x1, x2, x3, and the values are given there, 1.5 minus 1.2, 0.9. So as you can see, your inputs is not necessarily binary, even if we use very simple logical functions just to illustrate the principle of perceptron, but your inputs could be continuous. But in this case, your output would be a binary, because you can say your activation function is a step activation function. So it can be just 1 or 0. So I would invite you, try to work on this. And I would want to hear from you in the chat. What output are you getting for this particular configuration here? I'll wait for your answers in the chat, just to make sure you're able to do this type of calculations, what we've covered already, just to be a bit hands-on there. I think this is going to be also fun for you to really understand how a neuron activates, because like I said, the fundamental principle of any neural network is about the weighted sum, be able to apply threshold, and ultimately be able to apply the activation function to get the output Y. Yep, so try to work out. Remember the activation function, the step activation function in that case. So I just give you 1 minute, try to work this out, and just share with us your answers in the chat. I would want to see what answers you're getting for the output Y here. Just to give you maybe just to assist you in that. So normally what we do, we have to take the respective inputs, multiply by the respective weights. Like we said, just your weighted sum of inputs. So you have to take 1.5 times 0.7. So you have in a way x1 times w1 plus x2 times w2 plus x3 times w3. So you will have here capital X, which is 1.5 times 0.7 plus minus 1.2 times 0.3 plus 0.9 times minus 0.5 is your capital X there when you sum all these individual products. And then you would take capital X, subtract theta. So it's going to be in a case here, since theta is minus 2, it's going to be minus minus, so you have plus 2 anyway. So once you get this capital X plus 2, then you will apply it to your step function. Yep. So if that result there is negative, then your output will be 0. If that result there is greater than or equal to 0, your output will be 1. Yep. I can someone's getting 2.24. Yep. So you have to be careful. This is your capital X. If I just shift to 1 minute. Yeah, if I just shift to Octave here, you would all, I guess, know Octave. So if I just do the calculation there for capital X, so it is 1.5 times 0.7 plus 0.3 multiplied by minus 1.2 plus 0.9 multiplied by minus 0.5. That's your capital X. Yep. And then you will take your X minus theta, which is minus 2. Yep. So it's not working here. We can't put the minus. So it is basically it is X plus 2. No, I'm using X. Sorry. Yeah, it is X plus 2 anyway. Yeah. So we're getting 2.24. So that's your weighted sum of input minus your theta. But then you have to do this. I'm just writing it down, it won't work. So you have to work step of your answer. It may work if you have a step, it's not working, but you have to feed that answer. You've got 2.24 is only your weighted sum of input minus theta. But then you have to input that into your activation function. Yep. So if you look at the slide here, so your 2.24 is somewhere here. So 2.24, when you feed in activation function, you get 1. So your answer means is 1. Yep. So I can see many of you are getting 2.24. Yes, 2.24 is your capital X minus theta. But then this has to be fed in the activation function to get your output level. And as you see from the activation function, the output can be nothing else but 0 or 1. You cannot get anything else. What you've got here is actually your X plus theta, which is somewhere here. So it means your Y is 1. That's important for you to understand. So for any neuron you have, you would always first do the weighted sum. Yep. And then plus theta. Yep. Normally minus theta, but here it is minus 2. And then you will feed that answer into activation function to get the value. Therefore, Y is 1. That's good. Yep. So normally when I say activate a neuron, it means get the value of Y. Of course, X, capital X, and then capital X minus theta is an intermediate calculation you would do to get the Y. Now, if I also do the same thing for sine now, yep. So now, remember the sine activation function is very similar, except that your output can be 1 or minus 1. But of course, your capital X minus theta will be 2.24. So if you feed into sine activation function, you would again get 2 or you will again get 1. But if ever it was negative, then you would not have got 0, like for the step, you would have got minus 1 here. Yep. So as you can see, your output for step can be 1 or 0, and for your sine can be 1 or minus 1. This is why we use this activation function basically for classification tasks like true, false answers or accept, reject, or on-off problems, typically called classification or pattern classification problems. Let's look at this one now. Yep. So this one is called a sigmoid activation function. So as you can see, it is not just going to be 0 or 1. It is a continuous output between 0 and 1. Yep. If you do a simple mathematical analysis of that, you will see, was this x there, of course, is just a mathematical expression. If I replace your x there by 0, I will have 1 over 1 plus 0. This is why it is half here. Yeah, at the origin it is half. And then when your x goes to infinity positive, then you have a very small value here. This is why it is 1 over 1. This is why the limit goes to 1. And when x goes very large, but in a negative direction, minus infinity, then you have exponential of a very large positive value. Then it is 1 over infinity, you get 0. This is why it is bounded between 0 and 1, but intermediate, you have this nice change there. Can you work out the level of y for me? So now the activation function is not step, it's not sign, but it is a sigmoid activation function. You expect to get a value between 0 and 1. So you would apply exactly the same process you just got. You will get your capital X. Your capital X minus theta would be 2.24. And then you will replace your X here by minus 2.24. This is what you would get for your y. So basically it means in this expression, your small x here would be replaced by x minus theta, which you work out to be 2.24 already. So if you just quickly work this out, you can give me the answer in the chat. So what answer are you getting for the sigmoid activation function? If ever in that neuron here, you don't have the step, but you have the sigmoid activation function. Later today, you understand why we need the sigmoid activation function for certain type of neural networks. This will become clear. Yeah, I'm getting someone getting 0.903. So just a few more answers just to compare. It seems to be okay. Yeah, 0.904. I think that should be correct. We expect it. If you look at the profile, even there, if you get your 2.24 somewhere here, you expect it to be close to 1. Yeah. So just replace in that expression you have here. You just have to replace your 2.24. You should get something 0.904 like your friends are getting here. If I quickly cross-check that in Octave, so you will have 1 divided by 1 plus exponential of minus 2.24. Yeah, so it's 0.904 as you can see. That's correct. So well done. So it means now you know how to activate a neuron. Yeah. So whatever activation function I give to you now, you would know how to activate the neuron to get an output. And remember all the some problem here. 1 minute. Stop share. I'm getting some problem on my screen. Like I said in previous session, my screen tends to become color-coded, like we have all types of colors. I'm just shifting back here. 1 minute with you. Just showing the screen again. Okay, so I hope you can see the screen now. Now, next one, which I will show to you, is even simpler now. Remember, we had an activation function, y is equal to x. So it means this one, I will just do it for you. You've got your capital X minus theta to be 2.24. It simply says that y should be equal to x, so your y would be 2.24. Yep. So for the 4 activation function we've considered so far, fundamental step was to get capital X always, the weighted sum of each input with its respective weight. Overall, you get capital X. Even if you have thousands or even millions of inputs, you would do the same thing. You would do the weighted sum of each input with a weight, and then subtract 1 threshold, because you always have 1 threshold per neuron. And then the result you get, you will apply the activation function to get the output. And remember, we have only 1 output of the neuron. So important, these steps, it means if you get that clear, you know how to deal with 1 neuron. Okay. Let's move on now. Remember, when we trained the neural network last time, what I've shown to you was at the very end, remember this was your end function. I've shown that in Excel with you, and we actually basically repeat this training over and over again. And I've shown you that it converges. And this is the final result we've got. 0.3 for weight W1. We've got 0.2 for weight W2, and the initial threshold is written initial threshold here, but the final value of a threshold was 0.5 here. Yep. So the question for you is, once I get these weights there, what do I do with it? I think I gave the answer last time, but what do we do with it? Or how do I use it? So now you know how to activate a neuron. You should be able to understand if I use port 3 here and port 2 here and 0.5 here, and then you start feeding these different combinations here, x1 0, x2 0, you should get y to be 0. It means with these weights and threshold, it means your neuron is able to get the desired output. Let's just try one of them. If you take 0 times port 3 plus 0 times port 2, yep, so it means it is 0, both are 0, 0, but minus 0.5 because you have to subtract the threshold always. Your overall result is minus 0.5. Now, if you want to get such an output 0 and 1, it's going to be a step activation function. The step of minus 0.5 is 0, so I'm going to get this 0 here. If I do the same thing here, 0 times port 3 plus 1 times port 2 minus 0.5, I will get minus 0.3. Step of minus 0.3 is 0, so it is still good. This one is 1 times port 3 plus 0 times port 2 minus 0.5. So I get 0.3 minus 0.5 is minus 0.2. Step of minus 0.2 is still 0. And look at this one now. 1 times port 3 plus 1 times port 2, it means 0.5 minus the threshold. So 0.5 minus 0.5 is 0. Step of 0 is 1. Yep. So step of 0 is exactly where it is transiting into 1. So this is how, using these initial weights, I'm not saying it is unique. There are other combinations of weights and threshold which would give you the same truth table, but by iteratively adjusting the weights, how I've shown you last time, using the perceptron learning rule, alpha times x times e, where e is the error between your actual output you're getting from your neural network and d, yd is the desired one, we were able to adaptively change your weights and threshold to be able to converge to the desired output we want. Now, this graph is typical. This graph is showing to you how the error actually changed as we were iterating continuously. We found that initially we were getting some errors, which were -1, +1, but at some point after around 12, 13 iterations, the error started becoming 0 constantly. So as you can see here, a profile of how the error on the neuron or an accumulated error or the root mean square error, you can find different metrics for errors. This would be quite useful for us to see as you're training, as you're feeding your training set over and over again into the network, how come you can see if your error is reducing, means it is going in the right direction to converge to your desired training set. If not, maybe the network is not good enough. If not, maybe the perceptron is not able to classify the problem because it is not a linearly separable problem. Yep. So we'll come to that in a few minutes. Now, remember there were some diagrams I've showed you, scatter plot, where for the n function, we draw the 4 samples and then we are able to draw a line. So it's very interesting for us to see now the result we got. W1 was 0.3, W2, the 2 weights and the threshold. This is what actually allowed us to represent our n function correctly. So if we are able now to create that decision boundary, you can work it out like this simply because this is W1, so it is basically 0.3 times x1 plus 0.2 times x2, like W1 x1 W x2 minus theta is equal to 0 is the decision boundary. If you plot that, this is what we're getting. So you may say, yes, this is not very good because maybe I would have chosen a line here, but this is what we got. So when you train the neural network, this is what it converged to. And if you draw that in 3D, this is what you're getting. Yep. So these things, what you're seeing there, have been generated in MATLAB. So MATLAB have tools for you to deal with training of neural networks. Like Jyoti mentioned at the start, I'm going to just give some indications as we go along what sort of software packages you could use. So you could use MATLAB to do plots like this. As you can see, what MATLAB is doing actually, because we're using step. So this is your decision boundary here. Yep. And everything above here is plateaued if you want at a step value of 1. And everything on this side there is given a value of 0. So you can see your free samples, your free samples, your free instances in your n truth table are here in red, and a single one, which is there. If I show you the truth table again, this one here. So that single one there is actually on top, and the 3 zeros are red circles at the bottom. So this is basically what the neural network has done. In this case, as you can see, we have only 4 data sets, but it means all these combinations you have on this side would give a class of 1, and all these combinations you have down here of x1 and x2, it's a 3D plot, are going to be actually class 0. Yep. So it's quite a useful 3D representation. Now, this one we've not done it, but in the sheet I've sent to you, you also have the O function. Yeah, the O function, as you can see, is also linearly separable. So in O function, you have 3 class 1, and only one clause 0. So the training has been done a similar way, and this is the decision boundary I got, and this is basically how it is represented now in a 3D plot. As you can see, in this case, we have only 1 0, and the 3 ones are actually at a high level there. So basically, it's your decision boundary shown here from the top view. So this is your decision boundary. Yeah. So here, basically, this plot here is looking from top, and this is your single clause 0, and then your 3 clause 1. Yeah. So this is what the perceptron is doing, and this is your linear boundary, as you can see. Now, we come to the XOR now. Yeah, remember we said for any function which we can't draw a single line, and when we're covering that in the session 2, we've seen that it's impossible to draw a single straight line to classify the XOR. If you draw that on a scatter plot, you can't draw a straight line. Then we proposed some probable boundary, but definitely it's not linearly separable. It means a single neuron cannot solve it. But what if you use a sheet which I've shown to you, or if you use Python, or if you use MATLAB, and you try to make a single perceptron, try to learn this output, means you want to get this as a desired output, what would happen? So I've just given you snapshots here of the Excel sheet, and look at the error column here. And look at the inputs which you have here is simply 0, 0, 1, 1. So if you look at one epoch, yeah, it is actually your XOR function. 0, 0 is 0. So one is different, you have a 1, and then 1, 1, you have 0. Yep. So this is basically your one training set for the XOR. And then, as we said earlier, you will copy that many times because you will have many epochs. And of course, you have many iterations. Just pay attention to the error. The error after 10 epochs means 40 iterations, because one epoch is 4 iterations in this case. You have the error is not yet becoming 0. Yep. If you look at this column here, I've applied the perceptron learning rule alpha times x times e, as I've shown you last time. It is not converging here. This one is continuing now from epoch 19 to 20. Look at the error column. It is still not converging. From 20 up to epoch 30, it is still not converging. 40 also not converging. And ultimately to 50 is not converging. Now this is a plot of how the error is changing as I'm doing many iterations. As you can see, the error is just moving back and forth. It would actually never converge. And it's confirming to what I was saying to you earlier. A perceptron cannot be used to solve a non-linearly separable problems. The XOR is a non-linearly separable problem. Now, if you look at the history of AI, especially deep learning, you'll come across something called the XOR problem. This is the XOR problem. So when people came up with the perceptron learning rule, they were very happy because they've seen a perceptron could be made to automatically adjust any number of weights which you have. It's going to converge. But there were class of problems, and the XOR problem TP5 is type of problem which would not converge because, as we are saying, it is not linearly separable. So what should we do then? Yep, so it is found that the network does not converge as expected, but the N and O converge because, as expected, again, they were linearly separable. So this confirms the fact that a simple perceptron cannot represent the XOR function, and in general, any data set with a linear boundary cannot be drawn to separate the classes. To solve such higher complexity problems, you have to use now networks which have a if you want to have interaction between neurons, means not just one neuron. So one example of them is called a multi-layer perceptron. I've shown you one on the first day where you had a much more extensive network to what you're seeing here. Yep. But basically an MLP or a multi-layer perceptron. Let's spend some time on this one here. Why you have two inputs here? Because the XOR function has two inputs. This is why I have two inputs here. That is defined by your training set. If in my training set I had hundreds of inputs, I would have hundreds of neurons here in the input layer. Okay. If you look at the output here, why you have only one neuron in the output layer? Because I have only one output in my XOR truth table. It's only Q or Y. This is why you have only one output. So this, the input layer and the output layer, are defined by your problem or defined by your training set. Yep. Now, whatever sitting between your input layer and the output layer is called a hidden layer. Let's spend some time on that. Understand first thing why it is called a hidden layer. Second thing, here we're showing only one hidden layer. If you start programming in TensorFlow, if you start programming in Python, or even in MATLAB, you're able to use tens, even hundreds of these hidden layers, where you are really stacking all these hidden layers one after another, which would allow you to solve more and more complex problems. Basically, the hidden layer is introducing more non-linearity in your problem, And the very reason why we are choosing MLP is for this reason, because our perceptron is able to solve only linear problems. You want to be able to solve complex non-linear problems now, the boundary. So as you're introducing more and more of hidden layers, and of course, if you have two neurons in the input layer, doesn't mean you need to have two here. You could have put 3 here, you could have put 4. You can start increasing the number of neurons in the hidden layers, as well as increasing the number of hidden layers. Here I'm keeping it simple, just one hidden layer. Now, a word of caution here, you don't want to overcomplicate your network. If a simple network is able to solve your problem, you would go for a simple network for the simple reason, because of memory capacity and processing power. The more your neuron become more complex, the more difficult to train, first thing, the more memory space you need to store the parameters of a neuron. And if you want to now embed your neural network into microcontrollers and so on, it means you want to have as simple as possible for higher processing power and also less memory. So it is appealing if you want to look for a neural network which is able to do the work you want it to do, but as simple as possible. Okay, that's important to understand. Now, how training will take place? If you understood how training of a perceptron works, it is going to be fundamentally similar, but with some complication. In 1960, you have a person called Rosenblatt. He was the one who came up with the perceptron learning rule. And then from 1960 to 1970, it took 10 years to be able to come up with algorithm to train an MLP. So it was quite difficult to come up. People did propose different types of algorithms, from mathematicians to even AI scientists, even people from science. So different backgrounds, they've proposed different algorithms to do that, but it was not enabling them to do the training effectively. Now, what was the problem? If we look at, if you understood how the perceptron works, yep, there was only one neuron. Maybe to explain that, I would just have to revisit earlier what I said to you, and then we'll come to MLP. That's very important for you to understand that fundamental point. If I take this neuron, what did we do to be able to converge or refine the weight sphere and the threshold to be able to get normally Y actual? If I call that Y actual, it is what your network is giving to you. And then you have a desired output YD, what you want, which is in your training set. Now, when you're doing a training, you will take a difference of YD with Y actual to get your error. Yep, this is what a small e is. And then by taking the product of alpha, the learning rate, with your input. Now, if you are trying to adjust weight W1, you would choose X1. If you're trying to adjust W2, of course, you would choose X2. But in general, to correct any weight, you're going to multiply the learning rate by the input to that weight and by the error you're getting on that neuron. So that's why we call it alpha times X times E. Now, to be able to correct the weight and the threshold for a given neuron, it means you need to know the error of that neuron. How you get the error is by subtracting the actual error, the actual value you're getting from the desired value. So it means that error is fundamental for you to adjust the weight. So remember that very well. If I come to this MLP now, so how would it work if I show that to you? You would start with X1, X2, you would know the values. You would have values for all these weights here, W13, W14, W23, W24, W35. So all the arrows there stands for your synapse, remember, in your neuron, and they need to have values. Even W3, W4, and W5 needs to have values. So one question you might ask me, why this arrow here has no weight and why this neuron here has no threshold? Because these neurons 1 and 2, they are non-processing neurons. They don't actually process. They don't have an activation function in them. Their role is just to take an input and feed it forward. So these neurons 1 and 2 are just non-processing neurons. Whereas 3, 4, and 5, they are processing neurons, means they would have an activation function inside. In a few minutes, we're going to discuss on the type of activation function you need to use. And since they have an activation function, of course, they would have a threshold. And of course, they will have weights connected to them so that you can multiply X1 by W13, your X2 by W23 to be able to get capital X3 here. So that when you take capital X3 minus theta 3, you are able to get your weighted sum minus threshold, and then you'll apply activation function. This is why I started today's session with that exercise. Irrespective of complexity of the network you have, you will always take all the inputs feeding a neuron, multiplied by the respective weights, minus threshold, activate using the activation function to get the output here, Y3, I can call it. But Y3, of course, becomes the input to neuron 5. So you will take Y3 times W35. You will take Y4 times W45 minus theta 5, activate to get Y5. So activation starts from the left, goes forward. You find the weighted sum minus the threshold, activate using the activation function, get your output and feed forward until you reach at this level. Now, if you consider the XOR function, the XOR function which we have is a truth table with 4 data. It had x1, x2. So x1, x2, the combinations are 0, 0, 0, 1, 1, 0, and 1, 1. For these combinations, we have the respective output in your truth table. That's your Y5. It means when you come to Y5, you have an actual value, which is that you're getting from your network, and you have a desired value, which comes from your truth table. You are able to work out an error E. But what about the neurons 3 and 4? These neurons, yes, you have here Y3, which you're getting from your network, but you do not have a desired value. This is a complication. I'll repeat that again. For the neuron here in the output layer, you both have an actual value because this is what your network is giving to you. And you also have a desired value because the desired value comes from your training set. This is what is in your truth table. But what about the neurons 3 and 4? Let's call the neuron 3 is output is Y3. So this is Y3, and this neuron here Y4. So Y3 has an actual value because the network is there. You can work out an actual value, but you do not have a desired value. This is what's called a hidden layer. Hidden layer means you have intermediate states there, which is hidden from the real world because the real world would know the inputs and the output. But this one is inside your system. It's like in a black box. You do not have a state of these defined in the real world. And because of that, you do not have the opportunity. You cannot actually calculate the error for these ones. The moment you cannot work out the error, you can't correct for these ways because I need to multiply alpha times x times e. I don't have e. How will I correct for 1, 3 and 2, 3? Similarly, for Y4, I don't have Y4 desired. So I'm not able to work out the error for this neuron. I cannot apply alpha times x times e. So it means I can't correct W14 and W24. So this was a complication that they faced in applying the, so it means you can't apply the perceptron learning rule for an MLP because an MLP have hidden states. They have outputs for which we don't know the desired values, and it means you can't work out an error. I hope this is clear. So from here, how do we move forward? Yep. So to circumvent this problem, this is where I would need to go a bit at a high level because this is going to become very, very deep. I'm just going to give you an overview. Hopefully, if you read any material or take any course in the future, you would be able to go in depth. But I've explained very clearly to you what is the complication. We are not able to apply the alpha XE or perceptron learning rule. This is where the backpropagation algorithm come in. So if you hear that word in the future anywhere, backpropagation algorithm is an algorithm actually that has been developed by certain researchers to actually circumvent this problem, which we have just mentioned about the hidden layer neurons. Now, how the backpropagation network works, the backpropagation algorithm work, the name itself is saying here, you have to backpropagate something. Yep. What are we backpropagating actually? People have tried to backpropagate the error. So what can we do? Some people have tried. Once you have the error here, they've tried to apply this error backwards to multiply the error. Let's say you have an error at this neuron, you can multiply it by W435 to get the error for this neuron. Unfortunately, the value of the error itself, when you backpropagate it, it doesn't work. It's not a good state for the neural network to be used to estimate your error at this neuron. Like I'm saying, you need to have the error to correct for the weights. This is what we've seen last week. Delta W is equal to alpha times x times e. So if you want to correct weight W13, you need to have the error at this neuron. Okay. So what do we actually backpropagate? If you look at this third bullet point there, what we are backpropagating is not the error itself, is the error gradient. So we need now to define something called the error gradient. You can't backpropagate the error, it will not converge your network. Your weights will not be adjusted properly. People have tried this over 10 years and it didn't work. If you want, you can try it. It's not going to converge. Now, what this slide is showing to you here This error which you find here is at the output neuron. So don't worry about the subscript there. It may seem complicated. The K here simply stands for neurons on the output layer completely. The D for desired, the A for actual. We know that. So D come from your training set, A from your neuron. So for neurons on the output layer, you are able to work out an error because at this level, I know the desired and the actual value. So this one I can work out. This is no problem. Now, like I've said, you unfortunately cannot back propagate this error value itself back to get the error for the hidden layer neuron. It doesn't work. Now, how can we work out now the gradient of the error? The gradient of error, if you read that sentence there, it is calculated by, let me just say, since the error for neurons here cannot be computed, the gradient of the error is used instead, as the error gradient from the output layer can be effectively back propagated through the network. So it means now we need to understand how to work out the gradient of the error. This is by definition how the error gradient is calculated. So the error gradient is determined by multiplying the error by the differential of the activation function. This is pretty simple there. The error at the output neuron is known. So that's what I've just shown to you, the Y5 or the neuron 5 we've just seen. In this particular MLP, it was neuron 5. It means I have Y5. I can work out the error for this neuron. So how do I work out an error gradient? By multiplying the error I have at the output layer by the differential of the activation function. Now, this immediately tells you that for me to use an MLP, I need to choose an activation function which is differentiable because I want to get the differential of activation function here. This clearly says to you that I cannot use step or sign because step or sign is not differentiable. Step is just a grade of 0, infinity, and then 0 again. Same thing for sign. This is why you would need to use an activation function like sigmoid, not the only one, but you have other activation functions you would come across if you read this in this area. But one of the heavily used activation function is called sigmoid. And we've seen the expression already, 1 over 1 plus exponential minus x. And if you look at the graph of sigmoid, it is fully differentiable. There's no area there, which the grade, of course, is 0 initially and then 0 afterwards, but it is continuously differentiable. You don't get infinity anywhere. It means we need to differentiate this one. So it's more like a size for you. If you want to differentiate this function there, you would remember your chain rule in HSC. Yeah. If you want to find dy by dx for this expression there, but once you get to dy by dx, it's interesting for us to express the answer not in terms of x, but in terms of y itself. So I'll just give you 1 minute just to maybe allow you to practice or refresh your differentiation. If I want to differentiate this expression, what would I get in terms of x? But once you get the answer in terms of x, I would invite you to try to express it in terms of y itself, which becomes very convenient. It means if I have the output of a neuron, I can work out the differential of the activation function from the output itself. There's no need to go back to the input. So I'll give you 1 minute for that. Try to quickly work it out and see from the answer you get, are you able to express the dy by dx in terms of y itself? If you get answered, we're interesting if you share that in the chat. Yep, the answer is pretty simple actually. You see why we want to express it in terms of y, and the answer you get is quite, I would say, very neat. So it's not a complicated exponential answer. It's quite simple actually. So if you get any answer, do share in the chat. You can share with your friends. So try to find dy by dx, and from the answer you get, try to express it in terms of y. Any answer from you? You basically send the denominator in the numerator. So you have 1 plus e power minus x whole power minus 1, and then dy by dx, you have to apply chain rule. Basically, the minus 1 will come in front, and then 1 plus e power minus x power minus 2, and then multiply by the expression inside the bracket. So you have minus again e power minus x. So basically, you'd have something like e power minus x over 1 plus e power minus x square. Yeah, something like this. But it's interesting. I can see once someone says x equal to ln. Yep, seems a bit complicated actually. Maybe your answer is right, but there's a simpler way to write this actually. Yep. You won't get ln. Yep, I can see a right answer from there from Levish Polydou. So that's correct. Y into 1 minus y is a correct answer. Yep. So well done. If you just get the answer, of course, it won't be in terms of ln, like I'm saying. If you differentiate e power minus x, you get if you differentiate e power x, you will get e power x itself. Yep. We knew that from mathematics, but of course, it is e power minus x, and then you have to apply a bit of chain rule. The answer which Levish has given is correct, actually. Yeah. So I proceed ahead. This is what you would get. So this is the answer I was saying. I'm trying to dictate it to you. This is what you would get for dy by dx, and then if you start trying to express this answer in terms of what you had for y, you'd find that y times 1 minus y is actually the same answer here. Now, in expressing your differential of your activation function in terms of y, it becomes very interesting. It means from the output you're getting on the neuron, you are able to work the differential of activation function without using x. So this is quite interesting. Okay. So from here, let's move ahead. I'll be skipping some steps, unfortunately, on the backpropagation algorithm, because this would take too much time for us. I'm just showing you the main steps. So one of the main steps is there to choose an activation function, which is differentiable. We've chosen the sigmoid, and we've got an expression there for the differential. What this means, if I'm going some slide back here, some step back, if I got y5, yep, if I do y5 multiplied by 1 minus y5, I'm getting the gradient. I'm getting not yet the gradient, but the differential of activation function. Yep. So I'll repeat that again. If I have y5, yep, if based on the answer we've just got, we've got y into 1 minus y. So it means if I do y5 into 1 minus y5, I'm getting something called the gradient of the activation function at u15 is actually y5 into 1 minus y5. This is interesting. Yep. Now, how do I modify now? If you look at this result, that is very similar to the perceptron learning rule. Yep. That was alpha. Now, I've written y here. I'll explain in a few minutes why. But let's just come back to perceptron learning rule. It was alpha times x times e. Now I'm replacing my e by delta. Yeah, what is delta actually? Delta is the error gradient. If I go back one slide here, yep, just read that line again. The error gradient is determined by multiplying the error by the differential of activation function. You've just got the differential activation function, y into 1 minus y. If you take that multiplied by the error, you will get the error gradient, which you call delta. Yep, so we're going to introduce a new parameter called delta, which is simply equal to y into 1 minus y, which you've just got, but multiplied by the error. It's saying here multiplying the error by the differential of activation function. What you have here is a differential activation function. I need to multiply this by error. Yep. So this is what your delta is here. So I'm basically replacing my e now in my alpha times x times e. I'm replacing that e by delta. This is why you have a delta. Now, next question, why have y here? I get the answer from here. So let's say I want to, this is actually a bigger MLP if you want. Now, if you consider this neuron, where its input is? Its input is not X. Its input is the output of this neuron. So in this hidden layer here, I have the index J. So all the output in this hidden layer are going to be called Yj. So when I want to correct for this neuron, I have to apply alpha times X times delta. The X becomes Yj. If I want to correct this neuron here, it's going to be alpha times X. Then X would actually be this X because this is what's feeding this neuron. This is why you have a Y here, because this is the output from the hidden layer to the output neuron. But the fundamental rule is the same. Alpha times X times E has become alpha times X times delta now. Why delta? Because we are struggling with a hidden layer neurons. Okay. So this is basically very similar to the perceptron learning rule, alpha times x times now delta. Now, why became x now? Simply because now I'm correcting for these weights. When I correct for these weights, the input, of course, will be x, and now the delta will be called j, because now we are dealing with the hidden layers. Now, we don't yet know how to calculate delta. How we calculate delta, I'm going to be quite brief about that. We're going to take all the error gradients. So remember, we have delta here. We are able to work out the delta here because we know the errors. By calculating y into 1 minus y times e, because I know the e here, I'm able to work out the delta, the error gradient for all these neurons in the output layer. What I'm going to do next, I'm going to back propagate all these error gradients back to the hidden layer to estimate now the error gradients for these neurons. Because I have a problem still is I don't know the error for these neurons. I've explained that to you already. So how do I get an estimate for the error gradient on these hidden layer neurons? Is by back propagating all the error gradients back towards the input going for the hidden layers. So it means I'm able to estimate now the deltas for the hidden layers. And once I have a deltas, I'm able to correct the weights because this is what this is showing. Yep. So this is basically how the back propagation works. And I hope now it's clear to you when I talk about back propagation, what I'm back propagating, the error gradients from the output layer towards the hidden layers. If you had, let's say this one which I'm showing to you has only one hidden layer, but if I have two hidden layers, there's no problem. I'm going to back propagate from the output to the next one, and then from this one to the next one. So I'm going to keep back propagating to estimate the error gradients. Once I have the error gradients, I'm able to correct for the weights because this is what this expression is saying. It's very similar to a perceptron learning rule, but here, unfortunately, I cannot deal with errors directly. I have to find the error gradient because the hidden layer neurons have no desired value. I can't work out an error. Yeah. Now, what you're seeing here in front of you have been trained actually in MATLAB. So I've trained the XOR function. Remember, the XOR function could not be trained cannot be solved using a perceptron. So this is how the decision boundary looks like. This is your two high here, and then you have two lows in the valley here. So this is how the MLP is able to do this boundary for you. This is what the neural network is doing. It's creating this decision boundary, which is a bit awkward, I would say. It's not maybe what we expected when we draw it on a scatter plot, but this is what it is doing. It's having a valley in between here, where you have your two class 0 here and your two class 1 on top here. So this is how a top view would look like. So you have sort of a valley here, and this valley is at as a value of 0 for the class 0. Okay. Now this is about MLP. So I hope you've got a good indication here from a perceptron how you come to a multi-layer perceptron. That's important. Now briefly on convolutional neural network. Now remember right at the start of this 3-part series on AI, I did mention to you constantly we're trying to replicate the human behavior, how our neurons work inside our brain, and we're trying to replicate that. Now, when people studied how our how our visual system works, this is very important here. We have different parts in our brain which actually maps different areas or different capabilities. Like you have the motor skills, you have memory, and so on. There's a part at the back of our brain. Yep, it is directly related to our visual system, what's called the visual cortex. So people who have studied that have seen there are lots of similarities, how it works based on the findings there. They have, actually, as you can see here, in 1960s, Abel and Wiesel studied the cat cortex neurons, which is what I want to talk about. And based on the findings they've got, they've modeled it mathematically. Now, to understand how this works, you would need to do a bit of image processing. So in the future, if you have any modules on digital image processing, if you're already doing that, mechatronics or electrical or any from any background, if you want to understand how CNN works, you have to read a bit about image processing, a fascinating area. I'm really very interested about that. I had the opportunity to do a bit of image processing during my bachelor at the University of Mauritius, but also doing my doctoral study in UK. So when you learn image processing, you have a fundamental process called convolution. It's a very simple mathematical process where you have filters or kernels which can be moved on an image. Now, what's an image? Yep. When we talk of an image, we typically talk of pixels. If you go close to your television set or to your laptop, maybe you won't find it, but to your television set, you'll find lots of small squares, which are called pixels. So you have given number of pixels on the top as rows and columns. It's like a big Excel sheet if you want. You have small squares. Each of these squares can be individually powered and given different colors. What formats an image? This is basically what an image is. If you've done programming, if you are doing programming now or you will do programming in the future, it means an image is a 2D array. It's just like a table where you have columns and you have rows. Now, this is how our visual cortex also is tuned. It is in this way. So if you have any input, which is not of the form of vector. If I go back to the MLP, look at how the inputs are structured here. It's like a 1D vector. It's a long vector, which is 1D. But let's say your data is not in the form of a vector, it's in the form of an image. It's a grid, X and Y. Then it's very difficult for you. You can do it. I've done it myself. You can convert that whole image into 1D vector, and then you can use MLP, that's fine. But when you do that, you're losing information of the interrelationship with your pixel, because how you create an image is a relationship between the pixels, which you add together to create an image. So the moment you destroy that geometrical relationship between your pixels and you create a 1D array, as you can see here, to feed into your neurons, you're losing neighborhood information. This is the beauty of CNN. CNN actually works like this. So it still preserves this is what your input image is. And this is where you need to learn about convolution. You have masks, like if you read about image processing, you have things like averaging filter, you have things like the maximum filter, the median filter, averaging filter, sharpening filter. So you have different type of masks which would allow you to extract certain features from your image, like doing an averaging to remove noise, sharpening an image to really bring out the edges, things like this. So all these kernels will be applied on the image to get very powerful features from your image. As you can see here, one part of the image of this bird have been taken, and then you have applied different kernels on it. When you will do any modules and image processing, you will know exactly what I'm saying. What you will do on the input image, you don't need to destroy your image anymore here. You would use your input as a 2D grid as shown here. You will do some, what I'm saying, convolution. This is where the name convolution neural network comes in. When you apply these kernels, some of these kernels will have very prominent features. So this is what the pooling layer would do. It's going to extract all these salient features from your image. Once you have these, when you start with a big image, you will start getting smaller and smaller images. As you can see, it's not very big, but then you are sort of concentrating. People who do chemistry would know you're distillating the information. You're bringing it, after doing the pooling, you can apply convolution again. Really, you're concentrating the information. Ultimately, then you feed that to an MLP. So this part you know already. This is where your MLP sits. But before you come to your MLP, you have used your grid data, your image, if you want, your geometrical connection with your pixels to extract salient features from your images. And then you have ultimately come to an MLP, which can classify. Now, how can we use that? Let's say you have images of a process, you have images of butterflies, images of plants, images of birds, images of fruits. You want to classify them. Some applications, I can tell you, let's say you have different types of mosquitoes. You want to classify different types of mosquitoes. People who are experts in this area would know this picture is for, I don't know the name of mosquitoes, unfortunately, but let's say plants also. If you have different types of plants from the same plant family, this is what I want to say. If it is from different plant families, then it's a trivial task. But let's say you have very subtle things in your images which would allocate you to different classes. A CNN is able to automatically extract these features. You don't need to say anything. This is very important, what I've just said. When you use a neural network, you should not set the rules. You should not go and do image processing and extract the features, else it's not an intelligent system. You just have to give the images and tell the system which class this belongs to. For example, if you have lots of images of birds, you will say this is a bird. You have all your pictures. If you have 100 pictures of birds, you will say all these pictures are for birds. You have 100 pictures of dogs, you say 100 pictures, these are dogs. So how you do that, maybe you will call class 0. Let's say you give the label 0 to all birds. You give all labels 1 to dogs, all labels 2 to cats. You keep doing that. You feed that in your neural network. The neural network is going to train the weights and thresholds, same thing like you've learned already. Yeah, it's going to decide on the weights and threshold. Ultimately, if your CNN converges, when you feed new images of animals, it's going to tell you which class it is. So it's very powerful, especially if you have anything to do with images, or not necessarily images. If you're intelligent enough, if you can create your data, the grid data, images or a typical example. But if you have an application where you have images or any grid data, spatial data, and you want to create a learning engine to automatically classify these images into different things, it could be, like you can see here, not only 2 classes, true or false, it could be many classes, multi-category, but it typically goes for an MLP. And the previous layers, like I say, are convolution pooling, convolution pooling. Even the number of steps you would choose for convolution pooling is something you can play around, just like the number of hidden layers you have in MLP. So if your network converges, then you have a trained CNN, then you can use that to do classification, and very powerful for image processing. Really very powerful for image processing. So this is just to give you, if you want a general idea, what is a CNN, I hope you got that. So I hope if in mathematics or in any module on signal processing, any module you learn in image processing, computer vision, machine vision, you will learn about convolution. Yep. So bear in mind that this is really allowing you now to get into CNN, yep, at some point. The last class, if you want type of neural network, I want to present to you, but like I've said, you have so many other classes of neural network, but the main ones, you know already, perceptron, you know, multi-layer perceptron. I've introduced convolution neural network, and the last one is called recurrent neural network. This one is really for data with history. What I mean by this data with history, let's say you have a speech signal. A speech signal is not static. It's going to be changing. Now, same thing as say you're writing sentences. So it means you have a sequence of data, which is over time. If you have this type of data and you don't want just to capture the intelligence in your neural network for a static picture of your data, but you want it to carry forward, means when I'm speaking to you here, for example, it's very important in a sentence you hear me completely. It's not just one short part of a sentence, you will get the full meaning. You have to look at the whole sentence. So it means the intelligence in the sentence may be somewhere very early. When you look at a long paragraph, you need to look at the whole sentence to make sense of what is the meaning or what information needs to be conveyed. Yeah. So for this type of data, if you have any sequence data, I give you an example. When you're typing something in Google or on WhatsApp, for example, now you will find they are trying to predict what you will type next. So this is a typical example of sequence data based on the pattern of your typing. The sentence you're creating, they are trying to predict what you will type next. It's not just a static image. Yes, this image belongs to a bird. That is static data, but something which is changing. Let's say you have video frames. How the video frame is changing would lead to a different maybe output from your system, or how you're speaking is going to have a different prediction. For this type of data, which is sequence in nature, you have some examples given there, video image frames or audio clips, like I've said, or sentences consisting of words. So where you have sequence, and the sequence is important for you to predict what will come next, then recurrent neural network can be useful. I won't go in detail, this is how it looks like, because this would be a bit more advanced, but the methods you've learned already are applied here. You still have the concept of, as you can see here, xt minus 1, xt plus 1 are the sequence you have. So these are the different sequences. There may be different words occurring at different places in the sentence. There may be different sound that you have in a voice signal coming at different points in time. And these are the intermediate states to be able to predict. Yep. And then inside it there, you have a series of gates and activation function to decide which one needs to be remembered or not. So if you need to get into that, I would say it's exactly what we've covered, but with understanding you have already of a neuron and activation, and of course you're going to add some further principles there, you will be able to apply. So this is one type of recurrent neural network called LSTM. Yep. So this is very powerful to create this memory, if you want, to remember what was done some time back for me to predict what will come next. So like I said, there was sequence data. Yep. So you have few of that. One is called recurrent neural network, and one is called LSTM, which I've just showed to you. One is called GRU, gated recurrent unit. So you have 3 main types in this type of recurrent neural network. So again, just giving you a broad overview of it. if you want to go into depth of that, it would depend on your application. And for example, if you're doing image processing, I would say you will go more towards convolutional neural network. If you're doing general things, general data, you go for MLP, which is still very powerful. I would always encourage you to go for perceptron if you say classification task before to go for MLP. But if your application is really into sequence, then recurrent neural network would be something you would look into. Yep. So this is what I wanted to share with you up to now. I think we leave some time for questions. So back to you, Drishti.
Well, thank you so much, Dr. Guruchan, for another remarkable session. It's always indeed a pleasure to learn new things from you. I'm pretty sure that's the same case for the other participants. Well, I think we should now take the questions. We don't have any in the chat, I see, for today.
Maybe everyone understood it well, but just to recap, it's very important what we did earlier today on the activation and how to get a sum from a neuron and apply it onto activation function to get your output. If you understood that, it's already a very fundamental principle of neurons. So in the future, if people are talking about neural networks to you, it is actually permutations of that and trying different things, of course, but you have a good grounding now to learn new things.
We do have one question. So
I can
can
see.
Neural networks be used for processing images and videos?
Yes. If you've seen what we did earlier about the images, so if you have your data is in image form, you would go for CNN normally, but I have myself apply MLP with images where you would destroy the whole image and create, let's say, I'll give you one example. Let's say you have a small image, 30 by 30 pixels. Like I said, an image is typically grid data with columns and rows. If you take the 30 and 30 pixels, you make it become a 1D vector, it becomes 900 dimensions. 30 times 30, 900 pixels. You can just take all the pixel values, be it a grayscale or a color image. You can make it become a long 1D vector, and then you can feed that into an MLP. But like I said, this can work, but unfortunately, when you do that, you're losing lots of neighborhood information you would have in your image. This is where you're going to feed your image data as a 30 cross 30 pixels into directly. So you don't need to disturb anything. A CNN works with grid data. Yep. So it's well suited for processing images directly. If you have videos, then if you want to look for pattern in the frames, because a video is simply many images stacked together over time. This is what an image is, a video is. If you are looking for sequence in the data, then you're going to go for a recurrent neural network, like I've said, because there you want to look for maybe, let's say after 1 second or 1 minute of a video, you want to predict what will happen next. Then you have to use all the frames over that 1 minute. You have to capture, you have to have some memory of what happened, then a recurrent neural network would be suitable. Now, if your application is to take the different image frames and then consider each one individually to make sense of what's happening in it, not in relation to what's the different frames, but individually, then a CNN will still be used. It depends what you want to do. I can see one example, one question from Lavish. How can I build my own neural network? Which software language is best suited? So like I mentioned earlier, MATLAB is very good for that, but unfortunately, MATLAB is, of course, a paid software. But I would encourage you to learn Python. And with Python, you have something called Google Colab. Yep, I do run training programs. I'll be coming forward with more training afterwards. So I'll be advertising. If you're keen, you can join that. Yep, there'll be, of course, training programs coming in the future. You can build your own neural network from Python. And there's one very interesting platform called Jupyter Notebook and Google Colab, which is come from Google. You can, if you know Python, then you can apply it using TensorFlow. There are lots of nice examples out there on the web. You can build very small, from very small example from a perceptron and move to an MLP and ultimately CNN. Or interesting about TensorFlow, all the neural networks I've just discussed with you, being the MLP, the perceptron, or the convolutional neural network or the recurrent neural network are already programmed for you in Python library. You just have to use the function and then mention how many neurons would you have in the hidden layers. And you need to have a basic understanding, of course, of the topics I've discussed with you. And then you have to specify, of course, your activation function. You will have to specify what error metric you're using. You will have to specify certain other parameters, how many training would you do, at what interval do you want to get the output, and so on. But basically, Python and Google Colab are very good for that. MATLAB is very user-friendly, but unfortunately, like I said, it's paying. So if you can afford it, of course, as students, I think it's around $50, one license for student academic version. So if you want to learn, I think it's very reasonable. But in the future, if you are a professional, you're moving out from academia, your working industry, I think the license is easily 100,000 rupees. So then at some point you'll be cut off from MATLAB and you really don't have the option. You do have Octave, like today I've illustrated Octave to you, but Octave actually doesn't have all the libraries. It's still under development. I've been using Octave for quite a while as a freeware to replace MATLAB, but it's not fast progressing enough to catch up with the developments from MATLAB. Yeah, so MATLAB is really very good for that. But like I said, it's a paid software. It depends if you can afford it. But also one day when you're working, you might not have access to it. So Python would be a nice option to learn and as powerful as MATLAB, but maybe less user-friendly. But if you are someone who likes coding and you like having command prompts and typing, so it is good for you.
Well, I think that's all for this evening. No, we have another one. Do we have other activation functions other than those discussed in today's workshop?
Yeah, you have, I just give you some examples you can read on. There's one called ReLU or ELU. So when you start going more in details on the activation function, you will have there are certain problems. There's one called vanishing gradient. So over time, when you're accumulating your errors, there are certain activation functions like the sigmoid. It suffers because the gradient becomes 0. And that can be an issue for certain type of problems. Then there's one which we mentioned, which I mentioned called ReLU or ELU. So that's heavily used. There's another one called softmax, softsign. There are others out there which you can use. Yeah, but this is where software becomes very handy for the specific problem you're trying to solve. You can try different activation functions and see which one works for you. There's not one which fits all. You've learned about sigmoid. There's one called tanh hyperbolic sigmoid. Yep. So this one very useful. For sigmoid, you've seen it was between 0 and 1, the boundary. But then the tanh hyperbolic is between 1 and -1. But still, it is fully differentiable, and it actually is bounded between 1 and -1, very similar to the sine, but it is fully differentiable. The fact that the tanh hyperbolic activation function can go to negative values tend to accelerate the learning rate because it can go to negative values. So tanh hyperbolic is also a very interesting one.
What are the applications of AI in Mauritius?
I don't think it is within the context of Mauritius. Yeah, if you think about AI, it is going to be very generic for any application where you have data. You'll be able to apply it in the field of academia or even applications out there. Whatever, if I just recap on that, whenever you have any process out there which you don't have good understanding, you students, you'll be learning about control system or mathematical modeling. These are very good, very powerful methods, but can tend to be too complex or can tend to be too simplistic to be able to model a system. If you've learned control engineering, you would know that you're trying to get something called a transfer function to allow you to model a system behavior. We do that in chemical engineering, in the application, mechanical, pneumatics, fluids, even electrical engineering. But unfortunately, this model can be quite simplistic if you want to develop it. And once you get this model, it is very mathematical, may not be very useful. A neural network is well suited because it's like a black box for you. You're feeding input and output. You don't really worry about what's happening inside, but it's giving you the output you want. And once you get that, you can predict your output. So any problem where you have data, you can use a neural network, or any problem which you want to solve, but unfortunately you can't afford spending or you don't have you can't do it because there are so many problems out there where you can't mathematically model it. yeah, then you can start collecting data on the process, and then ultimately you can develop your neural network. Yes.
Do LSTM take a long time to process data?
It's not the training can be long. So when you're training it, it depends on the number of sequence you want to create. But once it's trained, it will be very fast. So the training can take a couple of hours if your data is quite extensive. But once you have your network in place, then when you activate the network, it won't take time. It's going to give you output almost instantaneously, because just feeding those signal into a sort of of nodes just to calculate and gives output. So once you train your network, it doesn't take time to activate. The training takes time because you need to continuously adapt your weights, like I've said to you. And depending on the complexity of a neural network, your weights can be quite difficult to tune. This can be an issue. It can take sometimes even days to converge. But once it's trained, then it will be very fast. Yeah.
Thank you, Dr. Guru-Chan, for attending to our queries. Well, I think that's all for this evening. And attendees, the link directed to the attendance sheet has already been posted on the chat box. Do not forget to fill in your credentials. And now, on an ending note, I'll let Yashil take over and deliver his word of thanks. Thank you from my side.
Yes, thank you very much, Reti. And we will now mark the end of this workshop on AI, which is also the end of our series of webinars. So considering the attendance, I will conclude that all of them were productive actually. Well, our activities does not stop here actually. We still have a site visit that we'll be doing at Metro Express this week and the following one for year 2 and year 3 students. Then I wish you all good luck for your exams, lots of sacrifice and hard work during these hard times. But I can assure you that the holidays will be totally worth it with lots of activities and events. So I would like to thank Dr. Guru-Chan for his dedication and passion for engineering, as well as his constant help and support for all our projects. I'm really grateful to the team that we have. So lots of names to state, 16 actually. So I will just drop the names in the comment sections right now. So thank you guys very much, because without you, all these events will not be successful. And I hope that you actually learn from them so that you can yourself organize them later. And I would like to thank, well, them via the societies, so the IEEE student branches, the IMechE student branch, Civil Engineering Society, Chemical Engineering Society, DACET Society, and the Oracle Club. So lastly, our most valuable asset, that is you, the audience, because we may organize events, but your presence, our blessings. So thank you very much and have a nice evening, everyone.
Okay, thank you very much. Have a nice evening, everyone. Thank you very much.
Dr. Guru-Chan, just a quick question
Yeah.
pour demain, le transport,